Hi, everybody. Happy Friday. We are going to wrap up our discussion about Gauss's law today. Can I just get somebody to confirm that you can hear me? People are
I can
putting.
hear you.
Perfect. Great. Thank you so much. Um, so, right, we're going to do a few more problems with Gauss's law. We're going to see how we can rederive some of the forms for the electric fields from some interesting charge distributions pretty quickly using Gauss's law. And then we're also going to play with how Gauss's law interacts with charged conductors. I think we'll probably get through most of the lecture material with some time to spare today. So at the end of class, I was going to open up the first written homework assignment and just talk a little bit about expectations there, because we've probably acquired enough knowledge at this point that you guys could think about starting to look at that assignment. So that's the game plan. Any questions while I get my screen sharing going? Okay. All right. Give me 1 second here. Okay, great. So let's go ahead and get going. So we're talking about Gauss's law. This is this fundamental law that relates charges to an electric field. And remember what it says. It says that the total flux through some closed surface, we're defining these Gaussian surfaces, these closed surfaces, some sphere or some cylinder or a box. And if we measure the flux through that surface, it tells us about the charge that's enclosed inside of that volume. And we were talking about we can calculate that total flux by looking at the electric field flowing through little components or little area components on that surface. Okay. So let's just jump into it and look at this particular problem. We've seen this one before, right? The electric field coming from a plane of charge. But let's see if we can use Gauss's law to find the electric field coming from an infinite plane of charge. Okay. And let's assume that we know how much charge is loaded onto that plate, and then it has a fixed charge density. I remember this surface charge density tells me how many coulombs per cubic meter I have in the or, per square meter, excuse me, I have on my sheet. Okay. So let's see if we can set this up here. By the way, I guess if people have feedback, I use this new note system trying to do some of the problem solving on this side application. If you guys have positive or negative feedback about that, or preferred me just opening a blank site in PowerPoint, let me know maybe in the chat or in the Slack channel which one is working better. I'd like to know that feedback. This application is a little bit easier for me to write in, and I can continuously scroll down, so I think it makes it easier. Okay, so what are we talking about? We're looking at an infinite sheet of charge. So let's go ahead and try to sketch out this problem. So here's what we're imagining, that we have a sheet of charge, and there's charges loaded up on this thing. So maybe it's positively charged. Okay, something like this. And remember, we're imagining that this sheet continues off in all directions for as far as we can see. So it's an infinite sheet. Okay, so how are we going to use Gauss's law to find the electric field? Well, we want to find, say, the electric field at this region in space. We're going to do the same thing we did yesterday. We're going to make some symmetry arguments to try to understand the shape of the electric field. And then we're going to use Gauss's law to help calculate the magnitude of the electric field. So this is an infinite sheet of charge. So remember, we talked about when we had the argument about its symmetry, if I had my sheet of charge and it was infinitely wide, it had to have this characteristic that I could rotate that sheet, or I could shift it left or right. right? Or forward and back. And if it's an infinite sheet of charge, I shouldn't be able to tell the difference between those situations. And we argued that the only type of electric field that satisfies that continuous symmetry is to have the electric field lines just point perpendicular to the surface. So we know the electric field by symmetry arguments has to point, right, perpendicular to this surface. And those electric field lines have to be uniformly spaced. They can't be more tightly packed at one area or the other, right? Or we would be able to tell something about, right, the geometry, right, the changing, right? It wouldn't have the same underlying symmetries as this sheet of charge, right? And the electric field is also present underneath this thing, something like this. Okay, so I have electric field that is following this spherical symmetry. So let's imagine I want to find the magnitude of the electric field at this point in space, and I'm going to use Gauss's law. Well, the first thing I need to do, right, I'm trying to apply this idea that the surface integral of the electric field dotted into some dA has got to be equal to the enclosed charge divided by epsilon naught. This thing, right, remember this implies that I have some closed surface. So I need to define my Gaussian surface. So what's a good Gaussian surface for me to pick here? Well, remember we said it's very convenient if the electric field is perpendicular to my Gaussian surface or parallel, because we know if the electric field is parallel to my surface or tangential to my surface, it contributes zero flux, right? If I have some surface and the electric field is running along the surface, it never goes through that surface, and so it doesn't generate a flux. And if I have the electric field completely perpendicular, then that dot product term just gives me that it's the product of the area times the electric field. And so really we could pick any kind of shape like this. We could pick some kind of shape. It could even be a wiggly shape where the top of that shape, say, is flat and parallel to the charge below it. And then underneath there's going to be a mirroring kind of shape, okay, that looks something like this. And then we're going to imagine just running straight lines down like this so that we have this kind of funny looking, almost cylindrical looking thing that goes through this. Okay, so that on the surface here, right, I would also have that funny looking shape here on the surface of my sheet of charge here. And now what we need to do is go and we need to sum up the flux through this object that we just made. Well, let's say we know that the area of this is A, right? This has the top of this three-dimensional shape we just defined and the bottom have cross-sectional area A. Well, here's the argument. The only thing we care about now is the flux, is the electric field that's going through the top and the bottom of that shape. Because the sides of this particular shape are parallel to the field, and so there's not going to be field coming in or out of the sides. So the flux through the sides, because of the shape we picked, we know has to be equal to 0. Okay. So if we want to calculate the total flux, it's just got to be equal to the flux through that top area A plus the flux through that bottom surface, that bottom surface area. And the nice thing here is we know that the electric field everywhere on this surface, right, we can imagine breaking it into small little dA windows. The electric field is going to be parallel to the A there. So when I do the dot product, I know that I'm just going to get, first of all, I know that I have a constant value for the electric field there because of the symmetry of the problem, and I know that the two fields are aligned. So this thing has to end up being just the electric field at the top times the area at the top plus the electric field at the bottom times the area of the bottom. Okay. And all of that has to equal my enclosed charge over epsilon naught. Okay. Well, look, the electric field at the top and the bottom, because again of the symmetry we see in the problem, we know these two, the values of the electric field at this, right, at this position and at this position had better be the same. So I can just replace those by one electric field because I know these are equal. So this is just like twice that common electric field magnitude times that area. And that equals to the total charge enclosed over epsilon naught. Okay. So one more thing, the total charge enclosed. What charge is that? That's the charge that's living on this portion of the sheet, right? It's the charge inside of my Gaussian surface. Well, how much charge is there? Well, the problem told me that I have a fixed surface charge density, right? This thing is telling me the number of coulombs per square meter that I find over that sheet of charge. And so if I want the total charge that's enclosed in my Gaussian surface, it's just going to be that density times that cross-sectional area that I see, that I have for that shape, for that two-dimensional cross-section as I go through there. And so if I just plug that in up here, I get something that tells me that twice the electric field times A has to equal eta, the surface charge density, times that area divided by epsilon naught. And look, the nice thing is that the areas cancel out. It didn't matter what the shape was, as long as it just had a fixed area, the same area on the top and the bottom, and as it was passing through the charge, those area terms cancel out. And I get something that tells me that the electric field has to have a strength like the surface charge density divided by 2 epsilon naught. Just exactly the same value that we calculated back in the previous chapter using superposition principle. We can get that same result using some symmetry arguments and Gauss's law. Okay? So that's good that they're consistent, right? I'm getting the same answers whether or not I apply the superposition principle and the empirical observation of a Coulomb form coming from a point charge, or I use this more fundamental relationship for Gauss's law that just says that the flux and the charge inside are coupled. Okay. All right. Right now, the hard part. So the hard part of Gauss's law is usually not calculating the integral. It's usually finding a clever Gaussian surface to, right, make that integral easy. Right, that integral can be difficult if you pick the wrong surface. But if you right, so you have to really understand these symmetries and what kind of shapes are going to exploit the properties of the electric field coming from fields that have that kind of shape. And that can be challenging for a lot of students, and even experienced physicists have trouble with these kind of with those kind of arguments for shapes that get more complicated than some of them that we're exploring right now. Okay. Let's try to do one more. Let's explore what the electric field has to look like around an infinite line of charge. And let's have you guys help me build this one up. Okay. So here's what we're imagining. We have an infinite line of charge that goes off right to infinity. And we're going to pick a Gaussian surface. I'm going to tell you that this is a nice Gaussian surface to pick, essentially a cylinder that is wrapped around the line of charge, with the line of charge going right through the axis of the cylinder, the long axis of the cylinder. So let's do this one. So here's the Gaussian surface, there's the charge. What about the flux through the ends of the cylinder? So I want to know, what does the electric flux have to look like going through the two circular ends of this particular shape? Let's go ahead and launch the poll. You guys tell me what the flux has to be going through the sides. Okay, let me end the poll. So 10 of you selected option A, that there's no flux going through, but then we had some of us selecting that there's right twice the right. So what are these different things? So here, this is the circumference, right, of one of those circular ends, and here this is the cross-sectional area of one of those ends. Okay. Well, let's see, how is the electric field oriented here? How does the electric field point? Well, we made this argument, right? We said if we had a line of charge, right, we know that I could rotate that line of charge and I could flip that line of charge and leave it unchanged. So that's what we're seeing here. So I need an electric field that has those same symmetries. And what we've seen a few times now is that electric field, we know, has to point radially outwards away from these charges here. Okay. So again, it's always kind of hard to visualize these things or draw these things nicely in 3 dimensions, but imagine I'm picking one spot there and the electric field kind of goes radially outwards. That means that all of the electric field lines, right, are parallel to a surface, right? If I take and I draw a plane like this that cuts through this, the electric field lines are all pointing just radially away. They're perpendicular to the surface here, right? All of these lines are supposed to be perpendicular to this object. They can't be tilted in this direction, right? Or when I flipped it, I would be able to tell that I'd flipped that object, and that can't be the case. So because all these electric field lines are parallel or tangential to the surface, right? I know when I do E dot A for that particular electric field, right? The angle, right? So how do we think about that? On these sides, we know the area vector is going to be pointing perpendicular to that, and that's at 90 degrees to any of those electric field lines that we see there. So this guy has to go to 0, right? The dot product is going to give me 0. What about the flux through the cylinder wall? What about the flux through here, through the main body of this thing? It's wrapping around, it's a cylinder wrapping around this thing. What's the flux through that part of the cylinder? I'm going to give you 5 more seconds. Okay, so we had a split decision between B and C here, with a few selections on A and D. So let's think about it. The flux, we know there's an electric field that's radially symmetric, right? So everywhere on this surface, there's this electric field that's pointing radially outwards, and it's distributed, right, uniformly over this surface. If I draw the electric field punching through this shape, it would look something like this, maybe. Okay. And so we know that 2 things. First of all, that electric field is perpendicular everywhere to this cylindrical surface because they both follow this cylindrical symmetry that we see coming from the underlying source charges. The other implication is because the cylinder is centered on the charge, we know that electric field, because of the symmetry in the problem, the electric field is the same magnitude everywhere on that surface. Okay. So that means that the flux that's going to be the integral over that surface of E dot dA, right, is just going to simply be that E times the area of that, right, of this cylindrical side here. So what is this? I need the area of this piece of paper that's wrapped up, right? I'm imagining that side of the cylinder is like a flat sheet that's rolled up, so I need the area of that sheet. Well, what is it going to be? It's going to be L, that's the length of that sheet. And then I need to multiply that by the circumference of this triangle, right? If I unrolled this thing into a sheet, if I have this thing like this, I would have L, and then I need to unroll it to get the length along this far side, and that would just be the circumference. So this has to be like EA, oops, sorry. This has to be like E times the circumference times that length L. And what's the circumference? The circumference is going to be 2 pi r. So this has to be like E 2 pi r L. And now we can look for that answer over here, and we can see that that looks like B. Okay. So now here's the question. Can we calculate what the electric field, the strength of the electric field is at this position, where at that distance r? Let's see if we can do that. So let's bring back up the notebook. And let's try to calculate the strength of the electric field there. Well, we know that, right? So for a line of charge, here's what we know. We know that the total flux has got to just equal the enclosed charge divided by epsilon naught. We just calculated the total flux. You guys told me that it was 2 pi r L E. Okay, great. So how much charge is enclosed inside of that object? Well, I have this infinite line of charge going off like this, and right in both directions. And remember, we could characterize that by something like the linear charge density. This thing that tells me how much charge per length that I have on this rod. And so if I want to know the amount of charge that's enclosed, right, Q enclosed inside of that cylinder is just going to be the linear density times that length L, right, the size of my rod. So I can just replace those here. That looks like the linear charge density times L over epsilon naught. And now I'm just going to solve this for the electric field. I notice that the L's cancel out of this, and I get something that just tells me that the electric field is equal to the linear charge density over 2 pi r epsilon naught. Okay. Again, this is just the exact same relationship we found using, that we found back in the previous chapter using superposition principle. Remember what we did there is we started with a finite rod, broke it up into tiny point-like pieces, picked a point in space above the rod, integrated the Coulomb, right, the Coulomb electric field coming from all those contributions, and then ran the limit of that rod as it went to infinity. And so you can see here we get the same result by exploiting symmetry, and we get it in about 2 lines, where the other one was some kind of messy coordinate system that we had to solve in 2 dimensions and do all kinds of complicated geometry. And we almost just get it falling out naturally from Gauss's law, right? We have to do a little bit of calculation, but as long as we pick the right Gaussian surface, we can really quickly get this electric field, the magnitude for the electric field. Okay. Right, the difference here is that we're assuming that we can correctly identify the shape of the electric field when we're picking these Gaussian surfaces by using the symmetry. Right? If that falls apart, if that idea doesn't hold, then you're probably just as good to use the superposition principle. But the point is we have both of these tools available to us to try to understand electric fields. Okay, good. So for the last material that I want to cover today, I just want to bring in the idea of trying to understand something about the electric fields coming from some conductors. Okay, so there's really no new concept here. This is just an application of the concepts. We've seen some of these ideas before. a conductor, remember, is an object that the charges, as a material that free charges inside of that conductor are free to move around. So if I have a conductor, and say I have a bunch of free electrons inside of this thing, we know they're all going to push on each other, and that Coulomb force is going to push all of these objects that are free to move in the conductor to the surface. They just repel each other to the surface. So for a conductor, all the excess charge always lives on the exterior surface of the conductor. Okay. And that's just because the charges are mobile. That's just the definition of a conductor. The charges are free to move, and because charges like to push each other away, they're going to try to get as far away from each other as possible, so they're going to push themselves to the walls of the conductor. Okay. So any excess charge resides entirely on the exterior surface of this object. There's another implication of that. It's that the electric field is zero at all points inside of the conductor. We can see that really quickly from Gauss's law. Let me erase all these little mobile charges. So they've all made their way to the edges of the conductor. So all of the charges are sitting on the edge of the cylinder. That means, say if I pick a Gaussian surface, say something like this, here's my Gaussian surface. Because all the excess charge is at the edge of the conductor, there's no charge enclosed inside of this guy, right? The enclosed charge in this Gaussian surface is equal to 0. That implies that the flux through this surface had better be equal to 0. And so the electric field, right? Remember, the flux is the field times the area. The electric field better be 0. Okay. So interior to a conductor, because there's no charge that I can, right? There's no Gaussian surface that I can find that will enclose a charge. I know the electric field everywhere inside of the conductor has to be equal to 0. Okay. What else do we know? The electric field has to be perpendicular to the surface everywhere on the conductor, and the magnitude has to be eta over epsilon naught. We're going to calculate that here by the end of class here, where that's the surface charge density. Okay. The fact that the electric field has to be perpendicular everywhere there is just a symmetry argument. It's just saying that if I zoom in here, I see that the electric field, right, in order for it to come from that charge that's hugging the surface, the electric field has to kind of map out the surface and point perpendicular everywhere. And it also says the electric field is 0 inside of any hole within the conductor unless there is a charge in that hole, right? So if I imagine that I have a conductor that's like a donut, so it's like a, I don't know, it's like a, right, like a tube of charge here. If I pick some Gaussian surface inside of this thing, right, if that's my Gaussian surface, again, there's no charge inside of it, so that means there's no flux coming through the object, and the electric field is 0 at that point in space. Okay, so let's try some problems related to a conductor and see if we can use Gauss's law to help us understand some of these questions. So let's imagine that I have a positively charged particle that's to the left of a neutral conductor, a neutral metal object. So I have a spherical conductor, has radius r, big R that you see there on the right. What's the electric field at the center of this sphere, at the center of that conducting sphere? What's the electric field at the center of the conducting sphere? Okay, I still see a few answers coming in. Okay, I'm going to go ahead and end the poll. So the most popular answer was D, that there's no electric field at the center of the sphere. Okay. If we flip back a side, this says that the electric field is 0 at all points within the conductor, right? And that's just a statement about the electric field always. So the answer here is 0, right? Just following along with that rules about conductor that we saw before. I have a conductor, conducting material. The electric field is always 0 inside of that conductor. Why is that? Well, what's going to happen here? That positive charge is going to pull negative charges close to it. And because they're mobile, they're going to get as close as possible. So they're going to all bunch up to this side of the surface. And that's going to leave, right, the positive charges, again, free charges can move in the metal to group up on this thing, right? The negative charges are going to shift to the right and get themselves as close as possible and leave a little skin of positive charge on the other side. But it's all going to live right on the surface of the conductor. And that means if I pick a Gaussian surface in here, the enclosed charge is going to be equal to 0, so there can't be any flux through that object, and so there's not going to be, right, there can't be any field inside of that conductor. What about this one? Now I have a conductor, some neutral metal, and it's got this void inside of it. It's got this kind of like pocket inside of the metal. And what I do is I put 3 nanocoulombs of charge inside of that little cavity. What's the total surface charge on the exterior of the metal? What's the total surface charge sitting on the exterior surface of the metal? Okay, let's go ahead and end the poll. So a lot of you selected B, but some C's. So let's see, what's going to happen here? Well, I have 3 nanocoulombs sitting there. If I imagine picking a Gaussian surface, right, that's inside of this, right, so imagine I pick a Gaussian surface like this. Am I going to have any flux through that Gaussian surface? Well, we've just made the argument that inside of a conductor, right, the electric field has to be equal to 0. So that Gaussian surface is living entirely inside of the conductor. That means the total flux, right, the total flux through that surface had better be equal to 0. And if the total flux through that surface is equal to 0, Gauss's law tells us that tells me that the charge enclosed had better also be equal to 0. So because this is a conductor, we know the electric field has to be 0 inside, and Gauss's law then tells me that the total enclosed charge also has to be 0. So that means I see a positive 3 nanocoulombs of charge inside of my Gaussian surface, and in order to get 0 total enclosed charge, I'll need there to be some negative 3 nanocoulombs of charge built up on the conductive surface inside of that cavity. But this was a neutral object originally, so the excess charge has to go somewhere. That means, right, those positive charges have to end up on the skin of the conductor because all the excess charge has to be on one of the surfaces of the conductor out here, and that has to be a positive 3 nanocoulombs because I need because I know the metal started out neutral, and so I have to have that the total charge on that conductor is still equal to 0. So I get a positive 3 nanocoulombs built up on the exterior surface of this piece of metal. Okay. So if we flip back, right, one of the rules of the conductor says that the magnitude of the electric field at the surface is the surface charge density over epsilon naught. Let's try to convince ourselves that that's the correct solution here. So let's bring up the notebook. Maybe. Sorry, now my iPad's fighting me. Okay. So here's what we're going to do. Let's imagine we have a sphere of charge. All right, sorry, a spherical conductor. And we're going to load it up with some charge. Okay, so let's say it has some radius r, and we're going to put some excess charge q on the surface of that charge, of that conductor. Well, we can calculate the surface charge density. We know the surface charge density, right? That charge is going to distribute itself uniformly over the surface of that sphere. And the surface charge density everywhere on that sphere is going to be like the total charge that I've put on the sphere, right? This has some Q total put on it, divided by the surface area of the sphere, right? 4 pi big R squared. And now what I want to find is, what does the electric field look like, right, at a point very close to the surface? So let's imagine here we're going to zoom in to that point in space on the sphere here. And we're going to try to use Gauss's law to find the electric field. So let's imagine that we've zoomed in enough that we're going to pick a small dA where, right, essentially this guy looks flat. We can zoom in close enough so that there's essentially no curvature to the sphere here. And so let's imagine that we place, say, a cylinder as my Gaussian surface through this position on the sphere, something like this. So right at this position, there's some charge that I'm collecting through this guy. Okay. And now I'm going to apply Gauss's law here. What does Gauss's law say? Well, it tells me that I have to do this integral of the flux contribution over that Gaussian surface, and that should tell me about the total enclosed charge over epsilon naught. Well, I know what the total enclosed charge is for that particular object. It's that surface charge density that I just calculated times whatever this area is, right? Let's say this has cross-sectional area A. That's how much charge is enclosed in that Gaussian surface, divided by epsilon naught. And this essentially looks like the problem we were just doing for the sheet of charge, right? That I'm gonna calculate, I'm gonna argue that based on symmetry, I know that there's no electric flux going through the sides of this cylinder because the electric field has to be perpendicular to the surface of the metal. And so I only have to worry about the flux through the top and the bottom of this cylinder. So up here, there's going to be electric field flowing through some cross-sectional area A. And so I'm going to get a flux contribution through the top of this cylinder that's going to be like E times A. What about the bottom here? What's the flux through the bottom of this Gaussian surface? Does anybody have any ideas? Maybe if you have an idea, you can type it into the chat. Now remember, we did this for a sheet of charge. Now for the sheet of charge, this was also E times A on the bottom, right? There was this electric field that pointed downwards away from that line of charge. What's the electric field here? How about this question? What is the value of the electric field in this conductor? Do we already know that? We've been describing it. What is the electric field inside of a conductor? Yeah, 0. I'm getting people telling me 0. Because I'm inside of a conductor, I know the electric field has to be equal to 0. And if the electric field is equal to 0, then that tells me that the flux through this surface has to also equal 0. So to get the total flux through that Gaussian surface, I know it's 0 through the sides, it's 0 through the bottom. So the total flux is just E times A. And now I can cancel out A, and I see that I just get that the electric field has to be the surface charge density divided by epsilon naught. We did this for a sphere, but it turns out if you set this problem up carefully, that this is true for any type of conductor, that the surface charge density right at the surface has to be like eta divided by epsilon naught. If you zoom in really tightly. Okay. So again, that's an interesting result we can get by knowing a few things, right? The symmetry and some of the underlying features of the shape of the field that have to come from those arguments, that the field has to come from the charges. And also knowing that the field internal to the conductor has to be 0, we can quickly find what the electric field strength has to be very close to the surface of the conductor. Now that's right at the surface of the conductor, right? As we get further away, the geometry, right, this approximation that we made that this thing is flat falls apart, and we would have to do a more rigorous calculation. But this is if I zoom in and I'm very close to the surface of the conductor, then essentially I get that the field looks like what I would get from a sheet of charge, but with the field just on one side of it because I have conductor on the other side. Okay. All right. Okay. That's all the slides I have for today. I'm going to pause here and just ask if anybody has any questions over today's lecture or Gauss's law, or any other things that have been bugging you about the first 3 chapters. And if we don't, then I think what I'll do is I'll open up Blackboard and could I explain the Jacob is asking, can I explain the superposition principle again? Oops. Sorry. Let me jump back to the line of charge here. So I think Jacob is basically trying to remember what do I mean by the superposition principle? How do we solve this from using superposition principle? Right, and the superposition principle basically said, we did this problem back in the previous chapter, that if I want to know the electric field, say at this point in space, then what do? I'm going to imagine taking this line of charge and breaking it up into a bunch of small pieces. And I'm going to imagine that they're so small that each of them looks like a point charge. And then I know that the electric field coming from each little piece of this thing, right, is going to follow, right, is going to look like whatever that tiny little charge differential is divided by 4 pi epsilon naught r squared, right, something like this, because and it's going to point radially outwards because it's like a point charge. And then I know at each position, right, I'm going to get a different electric field value here coming from each of these little, right, underlying point charges. And the total electric field would be like the integral of the electric field coming from all of those little point charge contributions. Okay. I don't want to go through that whole calculation again, but you can see, right, you would have to, that the electric field coming from each of those little points, first of all, is changing positions. So you have to do, right, you have to do some 2-dimensional integral. You have to find the electric field in the x direction and the electric field in the y direction separately, and those things, right? So that's what I meant by the superposition. Okay, good. I jogged Jacob's memory. Okay. And you can see that calculation, right? Remember that calculation? It was pretty nasty and it took lots of lines, and we, right, had to do integrals in x and y and figure out like some geometry and use sines and cosines. We didn't have to do any of that when we used symmetry and Gauss's law here. Okay, there's a question in the chat. So why is the electric field inside a conductor always 0? If you zoomed in enough to see the individual electrons, wouldn't you see those electrons push each other, pushing each other to be evenly distributed throughout the conductor? Okay. So what we're imagining, right? So where do I want to draw? Let me just get a blank page here. So let's imagine I have a conductor, something like this. And really the conductor starts and it's some neutral object, right? So we know it's made out of atoms. So let's see if we can explain this a little more concretely. Okay. So there's a bunch of positively charged nuclei sitting on this thing. And then there are a bunch of electrons that are free to move that are uniformly distributed throughout this conductor. Something like this. And initially there are equal numbers, right? If I just have a chunk of metal that's made out of standard atoms, they like to be neutral and I have some neutral object. Now if I were to take a bunch of extra negative charges and pour them onto this surface, okay, well, what happens? The extra electrons come in here and they, right, are going to try to repel these other electrons, and the net effect is that I'm going to, right, move all these charges around. So I can't, this would be nice as an animation, right? But they're going to redistribute themselves. They're going to spread out as Keaton says, they're going to spread out uniformly through this surface. But what does that do? Well, the positive charges didn't change. So what happens in effect is that central neutral piece, that central piece is going to be neutral, and I'm just going to end up with a little skin of extra negative charges because these objects are trying to push themselves as far away from possible, right? They're basically trying to configure themselves uniformly through the object. But those positive charges are still there, sort of canceling out the central, right, the central bits here, and I end up with excess charge on the outside here. What do I get if I had, right, if I did this other thing? Remember we just did this problem. Can I just erase this whole thing? Yeah, clear this. What about if I have a conductor, it's got a bunch of positive charges, and initially it has negative charges, something like this, and it's neutral. And then I bring, right, I had this problem where I bring this positive charge close by here. Well, then what happens is, as these charges are going to shift each other, these charges are going to kind of shift around here, right? So I'm going to bring these negative charges a little bit closer to this side, and the positive charges are going to be shifted a little bit to the other side, right? So the negative charges kind of move closer to the positive charge while trying to stay away from each other. And the net effect is then I got these two charge distributions that kind of just like separate a little bit, right? They kind of spread out apart. So what I end up with is something that looks like a little skin of negative charge over here and a little skin of positive charge over here. And then in the core, it remains a neutral object. And then as long as I'm maintaining that neutral behavior in the interior of the conductor, then I can use Gauss's law, the argument that we made in class, to see that the electric field has to stay zero. So you can try to convince yourself of this, like imagine uniform charge distributions and the negative charges are free to move and how they would separate. And you'll always get that you have this kind of neutral core to the conductor that requires that the electric field is zero in the interior. Okay, any more questions? Okay, so real quick, let me go ahead and stop my screen sharing. And just pop over to Blackboard really quickly just to remind you guys about the first written homework, and then we'll call it a day. So let me share my browser. Okay, great. Well, why doesn't it want to log in? Oh, there we go. Okay, so just real quickly to remind you guys that we have a written homework assignment that's due in a few weeks. And you can find it in the course materials section in Blackboard. If you go in there, you'll find the written assignments folder. And if you open up that, you'll find that all of the written assignments for the whole class are available. But if you open up written homework number 1, you'll see that's due September 22nd. So we still have a few weeks, but I think at this point you can probably get started on that assignment. So let's just quickly open it up. No, I didn't want to do that. Sorry. Let's open it up as a PDF so that it'll open in the browser. Okay, well, shoot. Okay, so if you open that up, you'll see that it's a problem about asking some questions about fields, okay? And you're gonna submit this through Blackboard. It's worth, right, I mean, there's gonna be 4 of these assignments. Your syllabus tells you the percentage that there is, and you can see here that there are sort of 2 problems that have multiple parts that are a little bit long, some are a little bit longer than the others. The first 2, so problem 1, you should be able to do now. This is just about particles, charged particles interacting with a field. And basically what I want is for you guys to submit, written answers to these problems. I want to see your work written out clearly. So you don't have to type it up. If you want to write it out on a piece of paper and use the submission suggestions that I posted online to submit a handwritten copy, that's totally fine. And I expect a lot of you to do that. But I do want to see, for each problem and each part, some prose and some discussion about your reasoning here. Now the second part has some asks you to do some things about electric potential, and we're going to start that topic next week. So it might be best to wait on problem 2 for another week, but you can certainly start on the first problem. Okay. So I just wanted to bring this to your attention and let you know that you should have the tools now to at least get started on this, so you don't have to wait till the sort of the 21st or the day before this is due. These problems can take a little bit of time, so try to work it into your schedule to make a little bit of progress on this as we go along. And if you have questions, bring them to class and ask them, and other people might have those same questions that they need clarification for. Okay, that's it for today, guys. Sorry for keeping you a few minutes late. I hope everybody has a great weekend, and we will talk again on Wednesday. So no Zoom lecture on Monday. All right? Thanks, everybody. Have a good one.
Thank you. Bye-bye.
Bye-bye.